Till yesterday, we talked about how, for virtual memory, one of the key challenges is to know which pages to swap, specifically when the main memory is full, because then the operating system need to evict a page and bring another page in its place. So today we are going to talk about exactly that, how to choose a place, a page to replace, to evict from main memory. So in page replacement algorithms, in general, the goal is that you want the lowest page fault rate on both first access and re-access. So essentially, you want the page fault to be lower. That generally means that you need to simulate whatever algorithm you give. Now, for now a standard method of simulating the algorithm, whatever algorithm you give, is to use something called a reference string. The idea is simple. The reference string is just a string of virtual page numbers, and you would just need to assume how many frames are in your memory. And using these two information, how many frames are in your memory and how many reference strings are there, you would guess, or you can actually deduce how many page faults will be there. Because a page fault will happen when the next character in reference string, that is the next virtual page number, is not in any of the frames. Let me give you an example with the very first simplest algorithm. So the very first simplest algorithm is FIFO algorithm. First in, first out, meaning whatever was put into main memory at first, it will be the first one to out. So essentially, we will take an example with a reference string here. Say this 7012030, etc., etc. All of these are virtual page numbers, and what this reference string tells is that first, whatever code you're running needs first the page, say virtual page number 7, then 0, then 1, then 2, then 0, then 3, and so on. We assume that there are 3 frames in main memory. So let's see that how can we calculate the page faults. So these are 3 in, so this is shown, these pictures, basically each one of those 3 boxes, this array, this column is a snapshot of your RAM. At the beginning, there is nothing in the RAM. So when the 7, this page was asked, you will bring in 7 and there will be 1 page fault. Then 0 will come. Again, 0 is not there, another page fault. 1 is asked, 1 is not there, another page fault. Then 2 is required. Now 2 is not in memory also, like so I mean in this snapshot, 2 is not in the memory, it's only 7, page 7, page 1, page 1. So you need to replace. And in this case, 7 will be replaced because 7 was first to be in the memory. Then it will be, you will affix 7 and put 2 in its place. Next step, you want 0. 0 is already in RAM, so no page fault. Then 3 is, so essentially in this way, in a FIFO way, you can deduce how many page faults are there by just a simple simulation. Clearly, how to track edges of the page, like because in the first in, first out, you actually need to know what is the edge. You would use a FIFO queue. Now, this is simple, but this is problematic, right? Because first in, first out queue would make the implementation extremely fast, and essentially all you need to do here is to calculate the page faults and keep a FIFO queue for your pages to know which one to evict. The problem, what Belady found was that in FIFO, there is an anomaly. He was writing a paper, and while checking the FIFO page replacement scheme, Belady and his co-authors actually plotted the number of frames with the number of page faults. Clearly, if you increase the number of frames, that is, increase the number your RAM, the page fault should be less, right? Because if you have, I don't know, 4 GB RAM, then low number of frames will be or pages will be in RAM. If you have 8 GB, many more number of pages will be in RAM. Very sure, see that is exactly not happening. When frame is equal to 3 for a particular reference string, that is a particular sequence of calling virtual addresses, the number of page faults is 9. But when the number of frame is 4, that is, you increase the size of your RAM, the page fault increases. So adding more frames, increasing your RAM size will cause more page faults. It's called Belady's anomaly. And the reason is, as we'll see later, that FIFO algorithm is what we call is not a stack algorithm. In a stack algorithm, essentially whatever is in your 4 GB RAM should also be in your 8 GB RAM, just like it should be. But FIFO is not a stack algorithm, so whatever is in your whatever is in 3 frames might not be included in 4 frames. It's not really an anomaly, but rather a property of FIFO. So clear, and also FIFO actually, as we'll see, that FIFO is not really very good in reducing the number of page faults. Now I made a claim that FIFO is not good and all these things. So you need to know what is good to know why FIFO is not good. So let's see what is good. Essentially, we actually the OS researchers, developers, they came up with the idea that let's actually make something optimal and then compare all other algorithms against that optimal algorithm. So people actually came up with an extremely elegant optimal algorithm, which is that at any instant, whenever a new virtual page come and a page request come and you need to replace a frame, you will replace the page that will not be used for longest period of time in future. Okay, so essentially it's just like you are in this optimal one, in this optimal algorithm. The view is that you know all the accesses over time, even in future. And at any given instant of time, like standing today, you will replace the frame or replace the page, essentially in this case, replace the page which will not be used among all the frames those are in memory, which will not be used for the longest period of time. So here, for example, again, we'll take 70120, this reference memory string, and 3 frames. First 7 was required, it was not there. So 7 will come in memory, 1 page fault. 0 is required, not there, 0 will be brought in the RAM, added 1, added 3 page faults. Now, for the next one, 2, you want to replace either 7 or 0 or 1. Now, from here to, if you look into when 7 will be used, you will see that it will be used for what, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So around after 14 references, 7 will be called. On the other hand, 0 will be called just right after, very soon, and 1 will be called before 7. So usually 7, if you then you will replace 7 because 7 is not going to be called anytime soon. So you can even by hand simulate this algorithm and you will find that 9 page faults are optimal. So in these cases, we only put the columns, the snapshots of RAM where there is a page fault. So if you just schedule this algorithm, then or basically simulate this algorithm, and you will see that there are only 9 page faults, and you can prove theoretically, that 9 is the optimal number, minimum number of page faults for any page replacement algorithm. So that definitely is great, but there's a problem. The problem is that in an optimal algorithm, you assume the God mode view. You know exactly what frames will be asked when in future. Think you are a West developer. You have no idea about the future, right? So you only know the current page references, what happened in, say, last day, last hour, last 5 cycles of processor. You'll know those. You don't know what is going to happen in future. Who can tell the future? So essentially, optimal algorithm is not practical because no one is a god and no one knows, much less than was developers, and no one knows what is going to happen in future. However, optimal algorithm is still useful for setting the baseline to tell how good or bad a page replacement algorithm is. Because you cannot be better than optimal, but you can closely approximate optimal, and that is our goal. So this optimal or OPT algorithm, in short, provides a very useful baseline. Now, how to approximate optimal algorithm? Essentially, the idea was, I would say, very elegant. I really love this idea. So in optimal, this algorithm is called, one of the most used, Linux also uses it, called least recently used algorithm, LRU. The idea is elegant. In optimal algorithm, you want to use knowledge in the future, which reference string or which frame will be referenced, will not be referenced for longest time in future. Why don't we just use it from the past? Replace pages that has not been used for the most amount of time. So instead of seeing in this direction in the future, you look into the past and say that which one is not used for the longest amount of time. So essentially, for each page, you will have a time of last use. And whenever a new page comes and you need to evict a page, you would replace the page which was used longest time in the past, back in the past. Again, in this reference string, here is the pictorial simulation example. Reference string 70120, 70 and 1, all three will give a page fault. For 2, you need to actually replace any one of them. And which one was used in the longest time in the past? 7. Okay, because 1 was just referenced before 2, 0 is referenced before 2, 7 is referenced in the past, most far away in the past. So 2 will replace 7. 0 is already there. Now 3, which one will replace 3? 2, 0, 1, and this frame 3, which will replace out of 2, 0, and 1. Let's see. So if this is like when 3 came, 0 was just asked before, so 0 cannot be replaced possibly. And then 2 is asked before that. 1 is asked or referenced longest time in the past. So 1 will be replaced. It becomes 203. And so on, it will go on, right? And you can implement it because you will have the last use for each page. And all you need to do is to sort, or basically not of sort. You want to find the minimum time of last use for each page. Now, if you do this LRU algorithm, like, if you just simulate it by hand, I already put it here and give you this example of using this reference string and 3 frames, you'll see there will be 12 page faults. It is definitely worse than this 9 page faults that our optimal algorithm will give. So it is definitely much better than the 15 page faults that the FIFO will give. So LRU is somewhere in between FIFO and optimal, and it is used pretty often. But how to implement this LRU algorithm? Now, in LRU algorithm, when I told this time of last use, I meant timestamp, like it was used in Friday, March 11th, 9:26 a.m. or something. The key is that you don't need such fine-grained time. All you need to know is that which one was referenced earliest in the past. So the most basic implementation that people came up with is basically a counter. So every page entry has a counter, and every time page is referenced to this entry, copy the clock into the counter. And that clock would be your machine clock. It doesn't need to be your wall clock. Machine clock means that how many cycles have passed. When a page needs to be changed, you look into the counter values and to find the small value. Now the counter have a problem, which is, I would let you guess for a minute, like, if you just have this counter implementation, like where the counter have the clock values, the machine clock values, the cycles that has passed, and then take the minimum of those clocks, what would be a problem? So one problem of this very naive implementation of having clocks is, any thoughts on that? The answer is simply that if you're using a counter for implementing LRU, then you need to, actually there are two problems. One I wrote here, one is something that you should think about. The hint is, the first one is that you need to actually search through a table, you need data structure, that there will be greater overhead. The second one is overflowing the clock counter values. If the clock counter values become really big, then it will overflow and you cannot really do any of this. Look into what integer overflow is and come back to me if you are not quite sure what I meant. This is because many of you are going to view this in the video. So integer overflow is a problem for counter implementation. Think how. If not, ask me over MS Teams, ask me in the next class, and I'll explain. But in any case, counter implementation has problems. So the second round of improvement, algorithmic and data structure based improvement, was stack implementation. So in a stack implementation, essentially we keep a stack of page frames in a doubly linked list. And whenever a page is referenced, we move it to the top, and it requires 6 pointers to be changed. Sorry. So why 6 pointers to be changed? Is there, let's just see if there is anyone. Yeah, there are quite a few. So any idea that why for a double link stack implementation, when you want to move one page to the top of the stack, why 6 pointers needs to be changed? The reason is that if you just, we need to break 4 at 2 pointers. Yes, absolutely, Anurag. Yes. So essentially, in the worst case, if you want to bring in a, sorry, if you want to bring out a page from middle of the stack and put it at the top, you need to break 4 pointers, right? 2 forward and 2 backward. And at the top of the stack, you need to adjust 2 more pointers, total 6 pointers. That's expensive. You need to do pointer arithmetic for 6 pointer arithmetic for each update. However, the good part is that you don't need to, there is no need to search, which was one of the big algorithmic problems for counter implementation. You just go to the bottom of the stack and effect it. In fact, LRU and OPT are case of stack algorithms, as I mentioned. This can be implemented by stacks. And a stack algorithm is essentially algorithm where n plus 1, if you have a n plus 1 frames, that will cover whatever is possible or whatever the reference string would be, whatever the content would be for n frames. Just to give you an example for use of this stack, say there is a reference string 470, so and so forth. So at this point, in this reference string, before you want to add 7, this is the state of the stack, right? So essentially, when 7 come, you want to put 7, this page, at the top of the stack. So you break, so you will just adjust this double linked list. You break 4 pointers, 2 between 7 and 0, 2 between 4 and 7, and you add 2 pointers on top of 2 to make this, to change the stack. Any questions so far? I mean, it's fairly straightforward, both FIFO, first in, first out. You all know FIFO queue, did stuff with it. The second one was optimal, the third one was LRU. And in LRU, we have two implementation, counter, and currently you have the stack implementation, which is still bad, by the way, because it's expensive. So the stack algorithm says a set of pages in a memory, n frames always subset of the pages. So it's basically give you this guarantee that there is no Belady's anomaly. Okay. Now LRU is expensive. No questions about that. Either you need to search or you need to have a double linked list, which will take 6 operations for each update. And there will be 100,000 millions of updates within an hour. So there are schemes to approximate this least recently used algorithm. For approximation, we would need one special bit called a reference bit, or R. For each page, see, there's an overhead, by the way, right? I mean, when you are adding one bit to one page, that means for millions of pages, you are adding one bit each. That, as you will see, it is worth it. So essentially, in this reference bit R, this reference bit R is set in the following way. For each page, associate a bit R and set R equal to 0 whenever a page is accessed. When the operating system by the operating system, any process accesses that page, set R equal to 1, meaning the page is referenced. This is yet another bit, I would say, that we talk about invalid bit, we talked about dirty bit, and this reference bit now. But using this reference bit, we can do fairly nice magic to speed up LRU and approximate it. Now here is a simple clock algorithm without using counter, without using anything. It is also called the second chance algorithm. It is extremely simple. You start with any page, so you need to evict one page. You have to find that victim page, right? So you start with any page P. If R equal to 0, that means that no one has read or written that page, and you can, then it's a good victim page. You replace the page P. However, if R equal to 1, that means the page is recently used, not a good candidate for now. So you reset the R to 0, saying that, okay, next time when it will come, then if R is still 0, then I'll replace it. Of course, if someone, some other process uses the same page again, R will be again set to 1. So, yeah. But the step 3 is that, so the page P is, if R equal to 1, Then you did not get the victim page. You set r equal to 0 and move on. Move on where? Move on to p plus 1 modulo number of pages. So why is it a clock algorithm? Because if number of pages is like you have n, then you'll go to 1, 2, 3, 4 dot 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 n, and then again start from 1. It is also called a second chance algorithm because say if you are going from 1, 2, 3, 4, 5, 6 dot 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 n number of pages, and each one of them has r equal to 1 in your first sweep. Then in your first sweep, you already set all r equal to 0. In the next sweep, you will possibly get at least one page which has r equal to 1. At least one which is r equal to 0. And you will evict it. So reference bit basically tells you whether you can or cannot evict a page. Nothing special. Now there is yet another modification, and this is a good approximation actually, but there is yet another modification. People considered that, people actually considered that evicting a page is sometimes expensive when dirty bit is equal to 1. Why? Because remember that we talked about that when you are evicting a page, you are taking a page from your RAM, putting into swap because there is no place in the RAM left. In that case, if dirty bit is equal to 1, then you have to write that page into swap space. If the page is dirty, you need to write it in the swap space. If the page is clean, you'll just discard it. So isn't it good, is it better if we can replace some clean pages? That will reduce the overhead. Page fault won't be as expensive. So an improvement that people came up with is, and see, this is like, and people mean that with developers, and they want the last bit of performance. And what they did is that in your step 1, when you're saying whether reference bit is equal to 0, also consider the dirty bit. And how do you consider it? Essentially, they told that consider the tuple, reference bit, and dirty bit in your scan and evict in the following order. If both reference bit is 0 and dirty bit is 0, which means that reference bit is 0, no process accessed the page in near past, and dirty bit is 0, that means there is no change in the page. Take that. No one has used it, and there is no modifications ever in that page. So you can just discard it. It's the fastest. Then you can consider 0, 1, which means the reference bit is 0. No one has accessed it in the recent past. However, someone has written it. In the far past, someone has written something in it. Someone means that some process has written something in that page. So if you evict it, you need to write it to the disk. But okay, you will do it. Then consider if it is referenced in the near past, which is 1, but then even then you will prioritize the dirty bit equal to 0, and the 1, 1 is something that you really don't want to affect. Okay. So essentially, these two algorithms, second chance and this improvement, is meant for just optimization. You want to improve the LRU by reducing the number of disk reads and writes, and also you want to ensure that you don't have to bring in the page again after you evict. So if someone has accessed the page recently, LRU says that it will be accessed again. So if r equal to 1 and you evict it, you need to bring the page again very soon. That will add up to your number of page faults, add up to your cost of reading the disk. You don't want that. So reference bit only tells that which page is possibly not going to access anytime soon because it hasn't accessed for a long, long time. It hasn't accessed for, I don't know, 10 clock cycles. You might, or 100 clock cycles, you might guess that it is not going to be accessed for another 10 at least. So any questions on this approximation using reference bit? Okay, so reference bit is one of the long lines of bits that basically makes things optimized, but then again, you need to use it carefully, per se, and smartly. What these people did with the second chance algorithm, and then combining it with 30-bit. There are other two algorithms after this LRU and the approximations of them. What are essentially counting algorithms, where for each page you will keep a counter. The moment someone references that page, you will increase the counter by 1. And based on these counters, there are two more page replacement algorithms to find victim pages. One is least frequently used, and the other is most frequently used, LFU and MFU. The idea is simple. So for each page, you know how many times it was referenced in main memory, right? If you want to replace a page, replace the page with the smallest count, which is the page which is never used. On the other hand, on the totally diametrically opposite side, the MFU algorithm tells that no, replace the one with the highest count. And the rationale is that the page with the smallest count is possibly the one which is just bought in. That's why no one has accessed it yet. So if you just remove the page, well, then you need to bring the page back again. You don't want that. None of them are used in practice, but they're good to know because they are used in some specific use cases and specific type of workloads. If there are some specific reference strings where MFU is pretty close to optimal, but those are extremely not standard. But you should know this exists. Okay, so with this, we answered our second ask, which was requirement 2, which is how to determine which pages to swap. Essentially, you swap when there is no free frame. You either use a first in, first out, or you use the optimal, where you will replace a page which is not going to be used in the future, longest time in the future. And finally, LRU, where you are going to replace the page which hasn't been used longest time in the past. No one is using it, so you replace it. We also talked about approximating this LRU and using the reference bits. Reference bits are just bits which tells whether the page is referred recently. 0 not referred, 1 referred. Now the final operating system challenge is how to allocate free frames to processes, both user processes and kernel processes. So before we go into this third requirement, any questions so far on understanding this page replacement algorithm? That is what pages to replace. Great then. Then go ahead and look into the lectures and come back if you have any questions. But these are important, just to emphasize, these are important concepts, as you might imagine. Like every operating system needs this page replacement and whatnot, and it will be good, it will be necessary for you to, as a computer scientist, to understand them. So take a look at it if you are not even understanding everything right now. We are here to answer any questions that you have when you go over it carefully. So let's move into third requirement then. After you decided pages to swap, victim pages and so on and so forth, so you found a victim page, you if it. Even at the beginning, you have a bunch, and then you feed a frame. Even at the beginning, you have a bunch of free frames. So the third requirement for the operating system for this virtual memory is how to allocate frames to processes. You have a bunch of free frames, great. How to give them to or divide them into processes? So essentially, there are two major allocation schemes: fixed allocation and priority allocation, and there are many variations of them. What is fixed allocation? So essentially, you have two variants of that. So in fixed allocation is basically for each process, you have a fixed function to give them an allocation, like how many frames they will get. The most obvious one, equal allocation. You have say 103 frames in this case and two processes, give each process 51 frames. There is one frame left, so keep some as free frame buffer. So this allocation is specifically what allocation we will talk about now. It is specifically for user processes. We will talk about the kernel processes and their allocation. That is how we will give frames or basically portions of RAM to kernel. That will come later. We'll talk about it, but later. For now, all of these are user-generated processes. First one is just give equal proportion pages to all. Now, it might not be very prudent. Your MS Teams and your just think about it. Your MS Teams and your what else? Your Notepad application. Both are having the exactly same number of amount of main memory. Your MS Teams will crash in no time. So the second idea is you do proportional allocation. So allocate according to the size of process. The code and data size of the process. So this proportional allocation is can be dynamic as degree of multi-programming or process sizes change over time, but the idea is pretty simple. If your SI is the size of process PI, then you find the total size of all the processes, which is capital S here. And if your RAM size is M, which is total number of frames, then each process will have the data will have number of frames proportional to its size. So allocation for PI is divided by AI is SI small si divided by capital S multiplied by M. It's just proportionally you are dividing M across processes. Proportional to what? Proportional to the process size. Here is an example. If there are 103 frames, one process has size 10 and the process size 127. Then the first process will get 10 by 127 plus 10, 137 multiplied by 103 frames, which is 7. And second process similarly will get 95 frames. Remember that these are all integer divisions and multiplications because you cannot really divide a frame saying like someone will get 7.2354 frames. That's not possible. So these are all integer multiplications and divisions. Okay, so for equal allocation and proportional allocation, after you look equal allocation, we have proportional allocation, but proportional allocation has a problem, which is that the size of a process might not be the indicator of its memory requirement or of its priority even. So some processes, so in Linux at least, processes have priorities. Look into nice values and so on, but essentially you can assign processes to priorities, which essentially means that which process will get a bigger share of CPU and RAM and everything. Okay? Some processes are more important than others. So the idea is that use a proportional allocation scheme using priorities rather than size. So if process PI generates a page fault, then select for replacement one of its frames. And which frame would you select? You will select the frame from a process with lower priority number. Essentially, when you want to want PI to give a frame, you'll take it from a lower priority process and give it to them. Now here, like when you say like take from process and give it to PI, that actually was a little bit interesting, because so far we haven't really talked about taking page from particular processes. We are always considering the pages to be managed by kernel, and irrespective of processes, we'll have all of our algorithm. Like in page replacement, we didn't really talk about particular processes and so on. So the reason we are talking about this part, taking frames or taking RAM from one process and giving it to other, because there are two flavors of allocation, frame allocation for user processes, global and local. So in global frame allocation, you replace globally, meaning that if you want to give a process P a frame because they want it, then you will select it from the set of all the frames. You will find the RAM, you look into all free frames, or you evict from any of the frames given to any of the processes. That's called a global replacement. The RAM, you are viewing you as a OS, as an OS viewing the RAM as a whole. The second flavor is local replacement. Each process has its own set of allocated frames, and you will move back and forth from one process frames to another. One way is that take lower priority process, take their frame, assign it to higher priority process. Generally, in practice, people use global replacement because there is higher throughput. And in local replacement, it gives more consistent per process performance, because now each process is happy. They have their fair share of frames, like unique share of frames. However, they might, I mean, in practice, local replacement leads to underutilized memory. If you give a process 50 frames, they are hardly going to use those 50 frames. That's what's seen in our real world. So essentially, in global replacement works better, higher throughput. You have a stash of frames, and you are assigning. Stash means like you have a big set of frames irrespective of processes, and you are, whenever a new process or a process requires a frame, you just take one frame from that stash, give it to the process. That's the global replacement. That is generally what is used. So hopefully up to this part, I mean, is sort of like this concept is simple about global and local, and then you want to assign frames based on priority, and sometimes according to their proportion. So all this page replacement and frame allocation that are expensive. You understand that, right? Right, this page fault and all these other things, they are expensive. And they're so expensive that gives rise to a particular challenge. Like so far we sailed through, like we'll solve the requirement one, we'll do page replacement, swapping. Page two, requirement two, we'll just do page replacement. Requirement three, we'll do fixed allocation. But nothing is so simple in real world. We run around with a problem called thrashing because of the very high cost of all of these things, of all this swapping pages and all this. So say thrashing is an extremely important concept, and you know what? When your computer hangs and freezes, it's possibly thrashing. It's common, it's nasty, and to be honest, there is a lot of work went into stopping thrashing. And that's one of the challenges. So what is thrashing? Thrashing is a very interesting phenomenon. So say if you have a process, your Chrome, it does not have enough pages. So it doesn't, if for some reason it couldn't really get the 2 GB of RAM that it requires. So the page fault rate will be too high. Okay? Because when would the page fault occur? It does not have enough pages, that is enough place in the RAM. So whenever it asks for new data, it asks for a new virtual address, you have to bring in from disk to RAM, that new page. And for that, you need to evict a page from RAM. So you replace the existing frame. However, you need to also quickly need that replaced frame back. So essentially, the process is just taking some page out from its memory, putting into disk. But then again, it is as a, then again it just realizes that it needs a page. It just wrote to the disk. It brings again the page from disk to memory by evicting some other page, and the cycle continues. So all the process does is just reading and writing from disk to memory, memory to disk to memory, memory to disk. And the weird part is, very weird part is that the process is not going to use CPU because it's mostly discrete write. So it will give you low CPU utilization. And suddenly the operating system thinks, oh, the CPU is not being used. I need more processes. So the operating system will increase the number of processes, like say it's daemons or all the processes, those are slept, those are suspended, they suddenly want to have a piece of the CPU. And there you have it. There you have it, the thrashing, where each process is busy swapping pages in and out from memory to swap to memory, because of inadequate number of frames. And thrashing is nasty simply because whenever a process starts to thrash, just reading and writing to disk, the operating system increases the load on the system by spawning or by waking up more processes, because the operating system thinks that CPU is not used properly. Those processes also needs memory, the memory that you don't have. So thrashing increases and the performance goes down. Effectively, you get a freeze. You see now, why is it nasty? Because the more and more you are going to do the swapping, the more and more disk IO will be done, the more and more process will come from your OS to clog the system even more. Here's a pictorial representation. So when you have it, the degree of multiprogramming is nothing but the number of processes those are running in time shared manner in your system now. So this is what a thrashing looks like. When you increase the degree of multiprogramming, remember these programs also need RAM, not only CPU. But from a CPU utilization point of view, whenever you increase the number of processes, the CPU utilization increases. No cycles left. CPU is always like running busy, busy, busy. But at some point, thrashing starts. And now all of these programs are really fighting for memory. And by fighting for memory, I mean that they're using page replacement algorithm to replace their pages to disk, and then again, bring those pages back from disk to memory again and again, doing only that. And the CPU utilization goes down because all these processes in the degree of multiprogramming, they are now just reading and writing from the disk, doing nothing. So none of your process progress. Now, we have to talk about, of course, this thrashing is a problem. I guess that many of your computer hanged, which is thrashing often. So we need to understand what is the reason for thrashing and how to solve it. So I'm not going to, so we'll cover thrashing and how to solve it in the next class. I'm not going to do it today. However, just an idea that we want to actually say is that demand paging doing smartly can actually reduce thrashing. And we'll talk about how in the next class. Please ask if you have any questions. Also, I'm stopping the recording.